Welcome back, teachers. Listen, I found a few homework problems that I found confusing at best when I did them, so I can only imagine what these feel like when you're going through. But I love them because they really challenge you. And these aren't necessarily the problems that you're going to be teaching your students, but they make sure you really understand these concepts. So I've picked a few that I think are like super challenging. So it says a child has fewer than 300 baseball cards. If he puts them in piles of 3, 5, 6, 9, or 12, and again, not just piles of 3 or just piles of 5 or just piles of 6 or just piles of 9. This is just random. Some of them in piles of 3, some of them 5, some of them 6, some of them 9, some of them 12. He has one card left over each time. How many baseball cards does he have? Now, a way to approach this is we need a number that 3, 5, 6, 9, and 12 divide into, and it would be the smallest number possibly. That's why it says it's below 300. So I need a number. We're looking for the whole number that 3, 5, 6, 9, 12 divide evenly into. But it talks about this leftover card. It has one card left over each time. So when we find it, we're just going to add 1 to it. Now, what frustrates me just a little bit is in the next section, and in section 4-3, we talk about a least common multiple. That's actually what's really happening here. We need a least common multiple, and the smallest number that all of these divide into is 180. Okay? If you pick anything smaller, okay, then one of these numbers is not going to divide into it. So 3, 5, 6, 9, 12, the least common multiple for all of those, it's kind of like finding a common denominator, right, is 180. But because of the remainder, we're going to add 1 to that, because no matter how we stacked them up. So the answer is 181. Now listen, I'm not going to go into serious detail about finding the least common multiple because that's in the next section. So right now you're kind of left to think, how could she possibly come up with that? One method is you could just list a ton of numbers that 3 divides into, like 3, 6, 9, 12, 15. You see what I'm saying? And then list numbers that 5 divides into, and that 6 divides into, and that 9 divides into. Again, 9, 18, 27, 36. Keep listing them. You're not going to get a number in common until you get to 180. And 12 is going to be the most restrictive, right? When you start listing all the, what we call multiples of 12, it gets big fast, and you'll see 180 is the first one in common. There are other ways to handle it, and you may know these ways. Again, I'm not going to show you here because it shows up in the next section. I almost feel like this problem should have been in the next section in 4-3. That's one reason I wanted to address it. But we take the 180, which is common to these factors, we add 1, and then that's going to give us our result, 181. Okay, y'all, on this one, I had to confess, I had like a what moment, and I almost got rid of it. And I even slept on it, and then I think it hit me when I was taking a shower. So here we go. When students asked their teacher how old her children were, she said, I have 3 children. The product of their ages is 72. Okay, what does that mean? If we multiply all 3 of their ages together, we're going to get 72. And it says the sum of their ages is the number of this room. Then it goes on, the children then asked for the door to be opened to verify the room number. I kept waiting for the room number. Y'all, they don't give it. Then Carly told the teacher she needed more information to solve the problem. And I agree with Carly. I need a lot more information to solve the problem. The teacher said, my oldest child is good at math. Then Carly announced the correct ages of her teacher's children. What are the ages of the teacher's children? Now, you feel free to pause it. I want you to go and ponder this thing for as long as I did. And then you come back. And if you get it, don't you even worry about watching this video. But if you're struggling with this, then struggle with me, and we're going to do this together. But please pause it and think about what I'm asking you first before you even listen to my explanation. So let's start with the easier thing to understand. We know that X times Y times Z, let's just say that's the 3 ages of her children, is equal to 72. So let's focus on the easier part. Let's see what possibilities multiply to give me 72. Now, one approach is you could do a factor tree, right, and get the prime factorization or the box. Let's do the box method to stay organized. I'm doing it on the far right of the screen. 2 divides into 72 36 times. 2 divides into 36 18 times. 2 divides into 18 9 times. 3 divides into 9 3 times, and 3 divides into 3 1 time. So the prime factorization is over here. It's 2 to the third. So again, 72 equals 2 to the third times 3 squared. Now we've got to think of all the possibilities of these numbers multiplied together. 3 of them. Notice how many prime factors. There's 1, 2, 3, 4, 5. So we're going to have to multiply some of this stuff together to get 72. So let's make a list of what these are. So 1 is right in front of us, 8 times 9, but that's not 3 kids, right? So that's not going to work. All right, so that we need 3 kids. So how about 2 times 4 times 9? That would work, right? 1 kid's 2, 1's 4, 1's 9. Is that the answer? Well, there might be other possibilities. Now, if we want to list the other possibilities, ignore this random stuff that I have here. I spent a lot of time listing all the possibilities. So what I was doing is I was looking at our prime number list. So 2 times 2 times 2 times 3 times 3. There's even a 1 involved there, right? Because 1 kid could be 1 year old. So I combined these in every way that I can imagine possible, y'all. And it took a long time, so I'm not going to do that here. This is just sit around thinking stuff. And you can get it organized where you start with a 1, for instance, and then a 2, and then you've got 2 times 2 is 4 times 3 is 12 times 3 is 36. That is one possibility. So I'm going to list them all for you and pop them back up. Okay, so notice what I've done. I've listed every way I could multiply these prime factors here where you have 3 ages. Notice that not different ages necessarily. I started with 1 and made the one on the left the smallest I could and the one on the right the biggest. And then I moved one of those factors of 2 over. You'll see, I kind of played around, and to where I think I have them all. Easily I could have left 1 out. But that still doesn't help. Notice it's supposed to add to be what the room number is. So if I added all these together, so you know you have 1 plus 2 is 3 plus 6 is 39. 1 plus 3 is 4 plus 24 is 28. 1 plus 4 is 5 plus 18 is 23. 23. 1 plus 6 is 7 plus 12 is 19. 1 plus 8 is 9 plus 9 is 18. 2 plus 2 is 4 plus 18 is 22. 2 plus 4 is 6 plus 9 is 15. 2 plus 3 is 5 plus 12 is 17. I know this gets old, right? 2 plus 6 is 8 plus 6 is 14. 3 plus 3 is 6 plus 8 is 14. 3 plus 4 is 7 plus 6 is 13. Here's the problem, though. And I was positive they left some information out. The children then asked for the door to be opened to verify the room number. They never told me the room number. And then it says, Carly told the teacher she needed more information to solve the problem. And the teacher said, my oldest child is good at math. And you're thinking, what does this have to do with anything? And this is what sleeping on it did for me. Okay? We don't know the room number. We know that the room number is the sum. Carly is smart. You hear me? Carly is smart. How do I know this? Because she came up with the idea of when she looked at the room number, she didn't have enough information. You know what that means? That she had more than one answer that equal to the room number. Look right here. That sums to 14 and that sums to 14. It's the only one that sums to the same number. All the others are different sums. None of the other ones match. And so that tells me that the room number is 14. And then Carly's teacher told her, my oldest child is good at math. How does that help? Well, look at the two situations. I've got 2, 6, and 6. Who's the oldest child there? There's 2 of them that are the oldest child. So if the oldest child is good at math, then it must be this situation right here, 3, 3, and 8. If the oldest one's good at math, there's only one. The 8-year-old is good at math, and then the other 2 are the same age. Again, it couldn't be 2, 6, 6 because there is no oldest child. There are 2 older children, and we know that there's a single oldest child because that one's good at math. Y'all, this problem blew my mind. I wanted to get rid of it, but it hit me how to do it, so I wanted you to see it. Now, keep in mind, I spent a lot of time coming up with this list that we have in pink right here. Easily, I forgot something, but it still worked out. When I typed in my answer, I had it correct. It still worked out that it made sense to me that the room number was 14, and that's why Carly needed to know more information, and then we could figure out what the answer was. Wild problem. Some of these make you work really hard. Let's do one more. All right, find the greatest 4-digit whole number that has exactly 3 positive factors. And the greatest, here we go, the greatest 4, we're just entering our answer over here. Okay, so how can we do this? Okay, so the greatest 4-digit whole number, okay, so that's very important. A 4-digit whole number that has exactly 3 positive factors. Now, there's something I want you to remember from the lecture. Remember when it had 3 positive factors? Whenever it had an odd number of factors, remember it was a perfect square? Okay? A perfect square. And to have 3 factors, then one of them has to be a 1, right? And then the number itself, and then this guy is the perfect square. Okay? That would give us 3 factors. This is the only way we can have 3 factors, because remember, every single number has 1 in itself as a factor. So to get only 1 more factor, we're dealing with a perfect square. Okay? Now it says has exactly 3 positive factors. So we need that number to be prime. The perfect square must be prime. You know why? Because if it's not, then that means that number has factors, which would also be factors of our big number. So the perfect square must be prime. This is the key to this problem. Now, the next thing we have to deal with is how big it is. So we are talking about the greatest 4-digit whole number. Now, greatest 4-digit whole number means it might be 9,999. Okay, but then 9,999 has a factor of 9. I know this right off the bat, so that's not the answer. Should you just keep checking numbers lower than that? I don't know. That's not the answer either. But here's what I want you to think about. Okay, this number is 1 bigger. It's not a 4-digit number, right? But it's the next highest number after a 4-digit number. Now remember, we could take the square root of that to figure out how many numbers we have to check to find if it's prime. We know this isn't prime. Okay, but how many numbers we have to check? So the square root of 10,000 is 100. So here's what we could do. We're going to look for primes less than 100. Okay, because when we square it, all right, it's going to give us our 4-digit number, and then the only factors it's going to have, the 4-digit number now, is 1, that perfect square prime number, and itself. So if I go back to my sieve of the Eratosthenes, where is he? Right here. Look, 97. That's the biggest prime number less than 100. Okay, and if I square it, so 97 squared, and get my pen to work, 97 squared is equal to, now we could do this using the standard multiplication algorithm by hand, but I'm going to save us a second. Cheating. Is 9,409. Okay, now if you break that down into prime factors, it's just going to be 97. That's it. Now, the divisors, not just prime factorization, but the divisors are 1, 97, and 9,409. It's only got 3 positive factors. Okay? So, again, the logic there was a lot. I've got a page typed up just to look and make sure we did this right. And there's the answer typed in. Yes, 9,409. But again, that comes from finding the biggest perfect square less than 100. Why do we pick 100? Because 10,000 is the smallest 5-digit number. That gave us a range to look at. And when we square 97, we get a big 4-digit number, the biggest we could possibly have, because anything bigger than that, y'all, is going to have more factors than just the 3 factors. So this was quite a doozy of a problem also, but I wanted you to see those 3 homework problems. The rest of them are challenging also, but I totally think you can dig hard and get them done. And if you have trouble, you just let me know and we'll talk about it. I hope you have a wonderful day, and I'll see you back for section 4-3.